Here's an illustration here of the SP. Now, again, these are the negative. These are the fresh water. Here's the SP here. Here is the sand, or the sand here. Again, this is the 16 and 60. This is the old style ES log type of thing. Here's the lateral log over here, the 16 and 64 inch, and then the 18.8. And you'll see here the highly resistivity, but here is now, again, when a lot of people first look at these, they say, whoop, that's a shale. No, that's not a shale. That is because of the RM relationship between the RMF and the RW. Here's the reversed, again, to summarize what I've just been saying. Again, the reversed SP, again, when the RMF is less than the RW, then the SP deflection is to the right. Again, it would be the reversed. No SP, it will be a straight line, and normal SP will be, again, is typically what we see in Kansas, Oklahoma, and we see it in the Williston Basin also. Again, this is basically just a calculation of the K factor as far as RMF, RW. And you read it, if you read these to determine the RW, here's the baseline. This is important when you do want to calculate what the RW is. Here, the inflection point. This is always a sticky point. Where do you put the top of the bed in an SP? And again, it's never, almost never a sharp bring out. It's not this. So, and again, it's the inflection point, which I think is pretty obvious after you once see a couple of illustrations, where the greatest change occurs. The summary, all right, that's natural occurring potential in the well which are developed opposite permeable beds. If you have SP, you have permeability of some amount. You have SP, you have permeability. It can detect permeable beds. It's an excellent correlation device used to determine values of formation water resistivity. And it's a good shale indicator, again, because you can compare it, again, depending on the RMF, RW. It's not developed in empty hole or an oil-based mud system. So if you've gone to the induction log, which a lot of people did because of oil base, then it doesn't work too well. Poorly developed in salty muds. So once we went to the focus tools, the lateral log and the micro lateral log, then in a sense the SP isn't as valuable. Here's again two things that sometimes I've had people remark on. Again, clay in the formation shaliness at the top will suppress the SP. So here's your SP, here's the good sand. Why is there the suppression, meaning the decrease occurring on the top? Hydrocarbons will do this, clay will do this, and many, many times if you have a dolomite on top of, like I said, in a super tidal zone in the Williston, we see it quite a bit, you will get, because of a dolomite, it will be sitting on top, and yet it's not, we'll say it's still the same reservoir. It's not a different formation, and so it should be treated just as it is. The effects of thickness and formation resistivity. Again, this is in here. I won't go into much detail again, but this compares what is nothing else. What does thinness and thickness of the bed, and what is the resistivity? How does it affect the SP? Here's just a thing I put in there just to give you in the chart if you're not aware of it. It's a way of calculating the RW from the SP. Very simple tool. I'm going to take a few examples. This was a gentleman with Schlumberger many, many, many years ago. And the date on it I couldn't tell you, but I'm just going to pick, there's 21 examples, but I'm going to pick just 2 or 3 to show you the difficulty. And mainly what I'm going to work on is mostly the lateral curve. And again, remember, it has an typically has an 18-foot, 8-inch thing. All right, now here's a freshwater sand, and look at the SP. This is going to be fresh water. This will be a water sand. Again, what's on this slide, if you can't, here's the microlog over in here. This is one illustration I ought to mention too. As far as digitizing, The microlog is a bad one to work with porosity. You can calculate porosity, but if you ever notice many logs, once you get into the porous section, say it's 10 feet, 20 feet thick, the curves of the 1 by 1 and the 2 by 2, so the two curves, we'll say, of the microlog, they pretty much are like this. They just go up and down. So unless you really believe that the porosity is the same throughout that whole section, you can't really use this as a porosity normally on digitizing. All right, here is again a water sand. You'll see, look at the lateral curve over in here. Lateral, about 1 ohm. I mean, it's almost no ohms. Here would be the 16-inch, the long normal, at around 8 or 9. So if you had to calculate, then here would be the RT. Now this one, you'll see this is a thick sand. So the 18 feet, 8 inches, doesn't affect this one too much. It's affecting a little bit. I've seen this many times. You'll get on top of a sand like this, you'll get 1 foot of higher RT. And immediately, I've done the same thing several times. You say, oop, wait, we got 1 feet of pay. Now you don't have any pay. This typically happens at the top. Here's again the same thing. Here's a 20-foot sand with an 18 feet, 8 inches. So this is a water sand. All right, now we're getting into the first example that I'll use. Here's the lateral curve. Look at this. I mean, here's again the 64 reading out at a certain depth. Here's the 16-inch, and here's this. What's wrong with this? These show that this sand or this reservoir is about uniform all the way through. And what's this lateral log, which is supposedly reading deep? What's it doing out here? Well, look at how much is this? This is 20 feet. So really what this is because of the thickness, in a sense, this is not an effective reading. So where do you take the RT from? Do you take it at the maximum down here, which is about 45 ohms? But then if you read the textbook, there's you take a 1/2, there's a 2/3 rule, there's all kinds of rules. I mean, this one, they say you go this far down, then this is a half, if it fits the rules. Then you take half the distance from here to there, so it's about here, and then you read 1/2 of that for the RT. Hogwash. This was done years ago. I can't believe that is true. I mean, how accurate can it be? It isn't accurate. If I was doing this, and again, I'm not sure it's absolutely, I would take the highest down here. Why would it be less than the highest reading that it gets in this reservoir? If I was to take an RT for this entire zone, and I realize that's wrong, because this probably doesn't have the same RT throughout this particular unit, but for analysis purpose, I would read the RT at this particular point, which is around 46, 47 ohms. This is a 0 to 50 scale. All right, here's similar type of thing. All right, this one got out of order somehow, but all right. Well, this is just a dense one. Let me go on. All right, here's another one. Here is a good example. Here again, here's the lateral curve here. The lateral is reading, it's about this 345 ohms. Back in here, the short is in this reading probably 30, and then the long normal is reading probably. So what do you want to read for the RT in this zone? I realize this is not rocket science, but something is causing this in here. So this is showing to me that this is an oil or gas zone in through here, and that probably this is the true RT, which is probably going to be, I'm guessing, about 20 ohms. Here would be 1 ohm, and so this probably is water. Here would be the transition.